the particulate model of matter. So let's start with this. All right, the first question, the wave pressure curve for acetone, ethanol, and butanol is given below. Starting at 40 kilopascals and 390 Kelvin. Short. This strategy could be used to separate butanol from acetone and ethanol. Okay, so we are at 40 kilopascals and 390 Kelvin. So that should be somewhere on here. Okay, and then what we want to do is we want to separate butanol, which is the orange curve, from acetone and ethanol. Okay, so okay, if that is the case, we need to be in this region. Okay, because when you're in this region, okay, let's say that you are at this point X. Okay, you will be above the curve with respect to butanol. That means you will be in the liquid phase. Remember, if you're above the curve, you're a liquid. If you're below the curve, you're a gas. Right? Therefore, it should be in liquid phase. But this point X is below the curves of ethanol and acetone. Therefore, those should be in the gas phase. In the gas phase. So that's the idea. Now, let's see. Decrease the temperature to 350 Kelvin. 350 Kelvin, and pressure to 60 kilopascals. So that would put us right here, which is great. This should work definitely. And decrease the temperature to 310 Kelvin. If you decrease the temperature to 310 Kelvin, while the pressure is constant, that means you will be over here. No, that is not going to separate ethanol from butanol, because both ethanol and butanol will be in the liquid phase if that's the case. So that is out. And decrease the pressure to 20 kilopascals. Let's try that. 20 kilopascals. So yeah, 20. While decreasing the temperature to 310, and 310 would be over here. So that will again will not separate butanol from the rest of the mixture. So that is out. Okay, we need to get to this region X if you want to separate butanol from the rest of it. So it's going to be just one. Okay, so this should be the answer. Let's try that one only. Moving on, select the temperature versus time curve that corresponds to the process of B to A in the phase diagram of neon shown below. Okay, so B to A. Take a screenshot soon. I can see more. No, okay, we'll deal with it. Okay, we're talking about B to A, process B to A. Let's think about that. Go. So when you go from B to A, okay, you are going in this direction. You're decreasing the temperature. That means you're cooling. If you're cooling, energy is released from the system. Okay, that much we know. Okay, now we're dealing with temperature versus time graphs now, right? So that means we're going to start at time 0. We're going to start at a higher temperature. Okay, and then with time, we're gonna after the process we're gonna end up at a lower temperature. That's the first thing. So we need to eliminate the first option for sure. Okay, so if this is the case, so we are over here at point B. This should be my temperature at point B. Okay, and then when you decrease the temperature, with time the temperature decreases, and then at the phase transition temperature, this is going to be freezing because this is the solid liquid boundary. The temperature remains constant. It's my TF for freezing temperature or melting temperature. Okay, but the time goes on because the system keeps losing energy to convert liquid to a solid. And once everything is converted to a solid again with time, the temperature decreases. So it should look something like this, and this should be my temperature at point A. It should look something like that. I think the second graph looks nice. So let's go check it out. Okay. So yeah, I like this one, not this. The third one doesn't look nice at all because it shows us the time does not change, but the temperature keeps decreasing. Yeah, I mean, it all takes time, okay, to decrease the temperature, increase the temperature, and increase energy or decrease energy takes time. So time has to evolve. And then fourth option does not make sense because we need to start at the higher temperature and end up at a lower temperature if you're cooling. So the only correct answer is option 2, which we have selected already. Moving on. Using the submicroscopic representation, which of the phases will have the highest average potential energy? Okay, so we're talking about I need to take a picture, even though this is not necessary, but anyway, let's try this. So highest potential energy means weakest interactions. We have the weakest interactions in the gas phase. So there's no doubt about that. The answer for this question in the gas phase. But I know that there's another version of this question where we were referring to the question was asking about the lowest average potential energy. And the lowest average potential energy should be in the solid phase if the solid phase was present. But in this case, we do not have a solid phase because of this randomness in these particles over here, right? This is not a solid phase. And if it is a solid phase, then we should have the particles more organized as well as closer to each other. All right. Anyway, because you don't have a solid phase, the liquid phase, what we have here is a liquid phase with the lowest potential energy. So we need to select liquid if the question was asking for the lowest potential energy. But in this case, the question is asking for the highest average potential energy. Therefore, we're going to pick the gas phase. Okay, without any doubt. All right, question for the phase diagram for neon is shown below. Estimate the freezing temperature of neon at 10 atm pressure. So 10 atm is 10 to the power of 1 over here. Freezing means we are talking about the liquid solid boundary, which is over here. And then the freezing temperature must be around, I don't know, around this value. I would say that it's going to be something close to 25 Kelvin, because each point is 5 Kelvin, so it should be 25 Kelvin. That's what I would pick. It's definitely not 40, definitely not 10, definitely not 80. It has to be 25. So we're going to go with 25 for that. Right, moving on. Imagine you have substances A, B, and C mixed in a container at minus 10 degrees Celsius and 1 atm. Under these conditions, the system contains, okay. All right, let's take another picture and then let's deal with that. Now you're given the temperature in Celsius, okay? So if you want to convert Celsius to Kelvin, we know that we need to add 273.15. So it should be minus 10 plus 273.15. Let's say 273 should be 263 Kelvin. Anyway, now we have that, and the normal means we're dealing with 1 atm, so that is great. Now, if you draw the temperature axis like this, okay, and then if we indicate what we have here, so we have the boiling temperatures of substances. So we have the lowest boiling point at 150 Kelvin. This should be the boiling point of A. No, it's boiling point of B. That's what I meant. And then we have C, boiling point of C, which is 225 Kelvin. and the boiling point of C, I'm going to indicate like that. And then we have A with the highest boiling point, and over here, 275, and that is the boiling point of A. Okay, and 263 Kelvin, which is the current temperature now, this different color, is in between 225 and 275. So let's say we are somewhere on over here. Okay, now this is the current temperature. It's called this T. Okay, now with respect to the boiling point of A, we are below the boiling point of A. It's like this. If you have water, the boiling point of water is 100 degrees Celsius. Okay, now it is analogous to being at, let's say, 80 degrees Celsius rather than 100 degrees Celsius. Okay, you know that if that is the case, A should exist in the liquid phase. Okay, and then when it comes to C, we are well above the boiling point of C. That means C should be in the gas phase. And then same thing with B. With respect to B, B is in the gas phase as well because the current temperature is well above the boiling temperature of B. Okay, so we have two gases. Yeah, it should be this option over here. Two gases and one liquid. Here we go. Moving on, question 6. Select the process that is taking place in the region indicated in the circle, by the circle, on the change in energy versus temperature graph that corresponds to process A to C. Okay. The diagram. Okay. Anyway, let's see A to C. Let's take a picture to deal with this. All right, so so we are going from A to C. We are heating things up while decreasing the temperature, which is fine. Okay, and then this is our temperature at point A. Okay, and then this is the last point is the temperature at point C. Okay, and then we start at point A, and then when you heat things up, so energy increases with the temperature, and then you are crossing, first of all, crossing this boundary over here. Remember, when we start reading these diagrams, we always start at delta E equals 0, because at that point we haven't done anything in the system. That's our beginning. Okay, that's why I started at TA and then went in this direction. Anyway, so then again, the first boundary that this process is going to cross is the liquid solid boundary. Okay, the solid is becoming a liquid. In this case, solid is becoming a liquid, and that process is called melting. Okay, then again we have other things. This is liquid heating up, and then this is the liquid to gas phase transition, and then this is the gas, and so forth. All right, so this is melting, and then there's only one answer with melting. I'm going to select that. That's it. Yeah, in that phase, when we are at that region, both solid and liquid is present. That is correct. All right, so let's select that. And moving on. Question 7, using the submicroscopic representation, which of the phases will have the lowest average kinetic energy? Now, here's the thing. So you are told that everything is at 5 degrees Celsius. Okay. I mean, or everything is at the same temperature. We don't care what the temperature is, but they are at the same temperature. Okay. If they're the same temperature, all the substances have the same average kinetic energy. Okay. They're talking about the average kinetic energy. Therefore, it should be the same in all phases. Okay. So that should be the answer. It doesn't matter what the phase is. It doesn't matter what the substance is. They will all have the same average kinetic energy. Okay, moving on. Question 8. The vapor pressure curves for methanol, water, and isopropanol are shown below. Rank the boiling points of methanol, water, and isopropanol at 20 kilopascals. Yeah, that's yeah, we should do that. Anyway, here's what we have. all right? The boiling occurs when the vapor pressure becomes equal to the external pressure, okay? And then the vapor pressure curves can be used to read the vapor pressure of that liquid at any given temperature, okay? So that's just a reminder of what this is. Now we're told that our external pressure is 20 kilopascals, okay? That means we are over here, okay? And then for methanol to reach that vapor pressure, for methanol vapor to reach that external pressure, it needs to be at this temperature, okay? And then for isopropanol, it needs to be at this temperature. And then for water, it should be, you know, what that should be actually at this temperature. So anyway, the point is, and then this should be the boiling point of methanol. And then this should be the boiling point of isopropanol. And this should be the boiling point of water. Okay, so we have the highest boiling point in water, then isopropanol, and methanol has the lowest. So it should be between the last two. And it seems like the fourth one is the correct answer. So we're going to select that. And that's our final answer. All right, I think that's it. So we're going to go ahead and submit our quiz. And when we do that, so 1 out of 1. There you go. That's how we get 100% for this quiz. All right, that's it, everybody. See you guys later.